Kim. I'm a graduate student at Busan National University and Division of Artificial Intelligence. Today I'm going to talk about multimodal transformer-based deep neural network for determining first positive structural variance codes. Structural variation are large-scale genomic changes such as insertion, deletion, duplication, and inversions. These involve genomic segments greater than 1 kilobase pairs. These structural variations are known to be associated with various diseases, such as, such as prostate cancer and neuroblastoma and Barrett's esophagus and autism spectrum disorder. To detect such as structural variation, a lot of software tools have been developed. Several major SB colors are summarized as table. They use spirit read depth, and read pair information from sequence alignments in BAM format. Although a lot of structure variation calling tools have been developed, they suffer due to high false positive rates according to Cameron's error and Kosugi error. And in general, they have a very strong trade-off between recall and precision. So precision dramatically drops when they get high recall scores. This results in low F1 scores according to Kosugi error. The first positive structure variations were determined by applying the following step in Cameron error and Kosugi error. At first, gold standard dataset were integrated from 10,000 genomic projects. They were examined by experts. And to evaluate such each SV colors tools, new sequencing datasets were obtained by sampling randomly at 50x coverage respectively from lists of high coverage dataset. For each new sample, alignments were generated using BWA-MEM. These alignment data were used for running SV color tools. Each SV colors by the tools was compared with the gold standard SV dataset. We labeled SV cores as true positive when it overlaps 90% with the structural variation in the gold standard. If it's not, it is determined as false positive. And if dataset had no gold standard, we labeled a structure variation core as true positive when it overlaps 90% with structure variant in other cores. Interestingly, there is a study for developing a tools to filter out false positive structure variations using the labeled data, which is called Divas filter. It converts read depths and read pairs and split read information to a rectangular image. Different deletion and duplication of HG002 and duplication of NA1 to H78. Then they build several classification models using CNN. It performs well on training data set, but they miss more than 10% of positive by determining them first positive on the test dataset. To improve F1 score of the SV filter, we designed a new model based on multi-modal transformer for determining first positive structure variations while maintaining high recall scores. This transformer architecture is suggested by Chai-Ya Hong in 2019. At first, we pre-processed alignment data to convert it to text, image, and signal modalities. In pre-processing steps, we embedded the reference genome sequence that observed structure variation region. Sequence data was embedded as 4-dimensional vectors per base pair. If they have soft-masked sequence, they are multiplied by 0.3. The soft masked sequence is meaningless compared to the normal sequence, so we scaled this sequence. These data are then used as text modality. And next, we convert alignment data to the image suggested by Divas filter. This method extracts spirit read with depths and with pairs using same tools and convert in that as an image like the figure on the right. In this figure, read depth is represented as red area and spirit read as purple and with pair as yellow. These data are then used as image data, image modality. Next, we convert alignment data to signal format. Like image modality, extract spirit read with depth and with pairs as per base pair. They are normalized from 0 to 1 value. After preprocessing work, we put this modality in 1D convolution neural network layer. For running transformer, we need to match the dimension of these modalities. So we decide the dimension of each modality using 1D convolution neural network. For example, like there are each modality. First, we pad each data to maintain data size putting in 1D CNN and calculating 1D CNN for each vector depending on the kernel size. We adjust padding size and stride for matching all modalities. And the dimension of output data is judged by the number of kernels. Each modality has the same dimension after calculating 1D CNN. And the next step, we put this modality into cross-modal transformer. In this layer, embedded modality text is considered as source modality and image as target modality. This source modality is calculated, calculated query weight and target modality, which are then converted as key and value before putting in the multi-head attention. And then query, key, and value are calculated using scaled dot products in parallel way. And take skip connection by adding in layer none. Next, by passing through position-wise feed-forward layers, then attention of the data is aligned and right. This course is repeated over D times. After that, we could get fused features from image to text. And next course, calculated fused features were concatenated when they are in the same source modality. This concatenated feature passed the self-attention transformer. This layer does the same things as the layer in the previous step, except that it uses as the same data to generate a query, key, value, and uses a scaled dot product. After calculating the self-attention transformer, each modality output was concatenated and it is passing through feedforward layers. After that, we can get output determining first positive structure variation or not. This slide shows the results used for training model. We generate short-read sequence data by randomly sampling HG002 and NA1 to A78 data to reach 50x coverage. HG002 was aligned with reference genome HES3075 and NA1 to A78 with GH38 using PWA-MEM algorithm. Gold standard dataset was obtained from 1000 Canon projects, page 3, which were integrated to high confidence structure variations. And then we code structure variation using NumPy, Manta, and Delhi. We trained the model using HG002 and evaluate using NA12878. Three figures show precision and recall and F1 score. Dark gray shows SD colors with no filtering. Red bar with filtered out first positive using deep SB filter, and green using our transformer model. Our model improved both recall and precision comparing to deep SB filter and resulting in higher F1 score. And we try to apply our model using data set in low coverage such as 20x coverage and 10x coverage. Our model shows still high F1 score than Divas filter. This tool in the figure is named IGB. IGB is commonly used to show how a read file has been mapped to a reference genome. At the bottom of the figure, the blue bar means the region of structural variance detected by SB colors. In the middle of the figure, the gray bar means a line depth position. And briefly, if the read depth is lower than the side, they set as deletion. If higher than the side, they set as duplication. These two figures show false positive deletion, while diversity filter missed to filter them out, but our model determined them successfully and false positive. These are examples of true structure variation. While diversity filter called them as false positive, our model remained them as true. In this study, we proposed a method to determine the false positive structure variations. Our model showed lower number of false positive structure variation than other cases. Structure variation with high and low coverage also showed good results. Multimodal running takes advantage of running low-level representation of structure variations, but due to early convergence of learning, overfitting increases and the tendency to misfit the test data increase. We are working on resolving this overfitting issue to obtain higher F1 score. Thank you for listening my presentation.
Okay, so we have 5 minutes for.
Hi, really interesting talk. Your query key and value vectors that you put into the multi-head attention module, are they the same size vector?
Yes.
Meaning that, so you took, one was set by the image and one was set by the text.
Yeah.
Which one did you make? How did you align them? Did you make the image like the text or the text like the image?
Yeah, both of them. We align text to the image and image to text and signal to text and text to signal. Yeah.
So you tried both?
Yeah, both. Yeah, both of all of them.
Okay, did one work better than the other?
The better is the most better is 3 case. Yeah, in this figure of them, the right green is the using all source. So that is the best height, the best score.
Okay, thanks.
Hi, thank you. When you're running the 3 SV colors, are they for different types of SVs, or are they combined?
Yeah. The 3 different SV color Manta and Longhai and Delhi.
Okay. So are you showing like combined data from all of them, or?
I combine all of them data and deletion redundant structure variation after that.
And then how much time would this filtering process add on to the SB calling pipeline overall?
Pipeline, for example, like converting image were like that, or running these models.
Yeah, I guess after running these SB callers and then running your step, how much time or resource?
Time of research is, I run about 7,000 data set, and the time, yeah, about 2 hours. About 2 hours. Yeah.
Thank you. Did you try to compare your approach with other meta methods that combine different SB, like survivor?
Yeah. Mm, can you repeat one more question?
Yes. So, if I understand correctly, I mean, this can be thought as a kind of a meta approach, right? And then so there's been some others not based on deep learning, other approaches. Did you try to compare the performance?
Yeah, I did.